A very good evening to all of you. We warmly and respectfully welcome you all to the first session of Isotopes organized by the Society of Chemical and Process Engineering students of University of Peradeniya. I am Sasini Pereira from E18 batch of Chemical and Process Engineering, and I will be the moderator for today's session. Let me start with a brief introduction to isotopes. What is isotopes? Isotopes is the newly launched initiative by the Society of Chemical and Process Engineering students, mainly focusing on mitigating the gap between their current academic curriculum and the substantial world of industry and higher education. This program consists of 3 elements. The first element is a talk series, which is a series of webinars with the industry and academic professionals. This is accompanied by a discussion series, which is a series of casual talks on the most interesting aspects of chemical and process engineering. And the final element is a series of workshops programmed to brush up skills in working with simulation software. The first talk was successfully conducted under the theme, The Role of Chemical Engineers in Combating the Climate Crisis, addressed by Dr. Tharindu Dasun Pereira. Isotalk 2 was carried out by Mrs. Sithila Dasanayake on the topic of ready to step out to the industry. The last session was on the topic of zero emission mining through process transformation, conducted by Dr. Nilanka Ekanayake. Also, we have entered the links of the previous sessions in the chat box. You can watch them leisurely. Today, we are going to commence the 4th chapter of the isoTalk series, isoTalks 4, to address the theme, Chemical Engineering in Biomedical Engineering. And now to begin the today's session, it's my pleasure and honor to have the opportunity to introduce our guest speaker today for isoTalks 4, Mr. Manula Rathnayake. Mr. Manula Rathnayake completed his bachelor's degree in Chemical and Process Engineering from the University of Peradeniya back in 2016. Then he moved to Melbourne to start his PhD in the Department of Biomedical Engineering at the University of Melbourne. During his PhD, he worked on understanding the macromolecular interactions in different types of cartilage for tissue engineering applications. After he submitted the thesis, he worked as an intern at the Knowledge and Technology Transfer team at the University of Melbourne. Then he moved to the industry and currently he is working as an R&D consultant at Acclime, Australia. So this is our guest speaker for the first session in isoTalks. And without any further ado, let's warmly welcome our speaker, Mr. Manula Rathnayake. Sir, the stage is yours.
Yeah. Thank you, Sasini, for the introduction. Please let me share my screen. Share sound. Share. Can you all see my screen?
Yes, sir, we can see clearly.
Okay, cool. Okay. So thank you very much for giving me this opportunity to share my experience in biomedical engineering. And thank you for the nice introduction as well. So today I'm going to talk about chemical engineering in biomedical engineering. So First of all, I want to tell you one thing, that you can just call me by my first name. You can just call me Manula. You don't have to call me sir. So that's all right. And also feel free to ask questions at any time. You can stop me and ask any question. That's all good with me. So yeah, so let's begin the talk. Yeah. So aim of this talk is to show biomedical applications which involve chemical engineering concepts and principles. So I have selected few biomedical engineering applications that I know of, and I have tried to relate them to the chemical engineering concepts that you might have learned during your bachelor's degree. So the topic is chemical engineering in biomedical engineering. But before knowing what is chemical engineering or biomedical engineering, I would like to ask you these questions. What is engineering? So that would be great if one of you can unmute and answer, or just type in the answer to the chat box. Anyone wants to try? What is engineering? Any answers? You can just type in, or you can just unmute and try to put up a few words what you think what engineering is. Yeah, nice answers, solving problems using math, physics, and chemistry. Yeah, thank you very much for your answer. And any other answers? Any other thoughts? Come on, guys. Okay. So I went to the dictionary. So look what dictionary says. So according to the Oxford Dictionary, it says the activity of applying scientific knowledge to the design, building, and control of machine, roads, bridges, and electrical equipment, etc. So this is what is in the dictionary. And then I came across this nice quote. I think this is displayed in EOE Pereira Theatre, if my memory is correct. Scientists study the world as it is. Engineers create the world that has never been. And this is a saying by a famous engineer, aeronautical engineer who lived between 1888 and 1963. Hungarian-born aeronautical engineer. So this doesn't mean that engineers are better than scientists or anything like that. This saying clearly says what is the difference between or the nature, and we are the people who would put it into the application. So this is what this saying says. And then as I feel, engineering is a practical way of solving real world problems with technology. So you can see I have bolded a few words: practical, real world problems, and technology. So sometimes there are problems and there are ideal solutions, but it might not be possible to reach these ideal solutions. So as engineers, we try to be more practical to solve these real world problems. So for me, it's all about solving real world problems in a practical way. And now let's move into chemical engineering. So guys, what is chemical engineering? You all have selected chemical engineering as your field of specialization. So just let me know what you think about chemical engineering, or what is chemical engineering. So I would really appreciate if one of you can unmute and say your answer. Otherwise, please type into the chat.
Chemical engineering is like building and designing plants and to scale up small scale reactions into large scale reactions to build a business.
Yes, nice answer. Yep. Any other answers? And thank you very much for your answer. Any other answers? Any other thoughts? So try to explain chemical engineering in 4 or 5 words. Like I'm looking for a really simple explanation, and it's related to basics that you learn at the faculty. So any other answers, like 4 or 5 words, you can explain what it is. Okay, no. So yeah, I'll move into my next slide. So it's, for me, I think it's chemical engineering all about mass balance and energy balance. So it is the very first thing you learn. And yeah, so it's basically mass balance and energy balance for different applications. So I have been very simple here because you all know what are the other aspects of chemical engineering, but I believe that mass balance and energy balance are the bread and butter of chemical engineering. So we learned about what is engineering, what is chemical engineering, and then what is biomedical engineering. So I went to this definition of biomedical engineering you see on your screen. So biomedical engineering or bioengineering is the application of engineering principles to the fields of biology and healthcare. Bioengineers work with doctors, therapists, and researchers to develop systems, equipment, and devices in order to solve clinical problems. Now you can see in the definition, I have bolded few words. So engineering principles, it could be engineering principles from different fields. And it says work with doctors, therapists, and researchers. You have to understand when it comes to biomedical engineering, it's a highly interdisciplinary field. You need contribution from doctors, therapists, and engineers from different fields, sometimes biologists like chemists, everyone. So this is kind of a teamwork actually. So it is a highly interdisciplinary field and it solves not just real world problems, it solves clinical problems, which is related to treating different diseases and conditions. To put this into more graphical context, I have put this diagram. So biomedical engineering is, you can see biomedical engineering, and then there are different fields of engineering. It's an intersection of all these fields. And there are many other fields, chemical, mechanical, computer engineering, and then biology, chemistry, and a lot of other fields. And then this is an interdisciplinary field to solve clinical problems, the same definition that was in the previous slide, but in a more graphical way. So I want you to understand that even though we divide engineering into different disciplines, it is because it's easy to learn when it is divided into different fields. But when it comes to the biomedical engineering, those fields come together in order to achieve one goal or to solve a clinical problem. Let me go to my next slide. Yeah, so I have intentionally left this slide blank, so you will have to listen to me. So next, I'm going to explain different applications of biomedical engineering and how they relate to chemical engineering and how can we use our chemical engineering background to solve this problem. So I will be talking about only very few applications. First thing is I will be talking a little bit more about tissue engineering because it's related to my background. And here is the tissue engineering. So have anyone heard about what tissue engineering is or regenerative medicine? So just type in yes or no, please. Have you heard this word before, tissue engineering or regenerative medicine? Yes, yeah, I can see. Yeah, cool, yeah. Yeah, there are like few people who have heard the word, which is really nice. So I will try to avoid, throughout this talk, I will try to avoid use of a lot of medical or biomedical terms, and I try to relate into a very layman's language because that everyone can understand. So I just think about this scenario that I'm going to show you. So imagine you have a broken car or a broken car part. What you are going to do. So if your car is broken or a bicycle or whatever, you're not going to throw away the car. First, you try to find, replace the broken part. You will go to a mechanic and ask to fix the vehicle so you can use it again. And think about our human body. When it comes to human body, what happens if our lungs or another tissue fails? What happens if our liver fails? heart, lungs. It could be any organ or any tissue in the body, and what would be the consequence? You could die. So failed tissue organ and can we simply replace the failed organ? Can you just replace the failed organ? Actually, you can't simply replace it. You can't do it because there is no way to buy your organ in the market. There is organ transplantation, but you have to find a donor and then you have to match a donor. And there are like a lot of tests and there is no guarantee that you will find a donor in time. So tissue engineering walks into this issue to solve these real world problems. How do we give a solution to unavailability of the tissues or organs when they are failed? So let's look at more about tissue engineering, like more definition, scientific definition. So tissue engineering is artificially creating body tissues using cells. So it's like taking cells and creating the tissues with human intervention. It could be in a laboratory or by other means. And then once we create a tissue in a laboratory, it should be able to restore, maintain, or improve the functions of damaged tissues or whole organs. So this is very important thing. Think about this car, like car part replacement. If you are going to replace a car part, you have to match it with the car model and the other specification, or whether it's the price of that car part and how it will be going to there, and it will be whether it's a suitable fit to your car. And it is same in tissue engineering as well. If you are going to replace an organ or a tissue, this replacing the novel tissue should be able to replace the function. Can it bear up the same mechanical loads as the natural tissue? So there are like a whole lot of problems like this. So there has to be like the novel tissue has to be mechanically competent to maintain or improve the functions of the damaged tissue. And here is a more like definitive explanation of the tissue engineering, or definition I took from the reference you see here. So tissue engineering is an interdisciplinary field. I won't highlight this, it says interdisciplinary. So that means the people from different backgrounds will contribute. That applies the principles of engineering and life science to develop biological substitutes with the purpose of restoring and regenerating damaged or injured tissue. So this is about, as I said at the beginning, it's about replacing the damaged and injured tissue. Whether it's an easy thing to do or a hard thing to do depends on the type of the tissue and the organ we are looking into. And today I'm not going to talk into the challenges of tissue engineering or anything like that. I will be talking you through the how as chemical engineers we can contribute to the field of tissue engineering. And next slide, our video. So as you saw in the video, so there are a few important factors for tissue engineering. One is engineering cells. So there could be different cell sources, and the selection of cell sources is a very important key factor in tissue engineering. It could be stem cells, it could be cells from the original tissue. And so depending on your application or the technique you are going to use to create your organ, you will select the cell source. And then there is engineering materials. And I believe this field is like engineering materials, the field that chemical engineers can contribute a lot and are contributing already. So there are different growth factors, novel chemistries, and biomaterials that can be developed with the material science knowledge we have. And it's a very important thing, like a very key thing is biomechanics of the tissues, like how physical forces sometimes interact with those tissues, and trying to understand the responses of cells to those external forces. And these are important in creating a tissue that can replace a damaged tissue. Like it should be functional, as I said in the beginning. So we have to understand all of these things in order to create a tissue that can replace the damaged tissue. And then there is engineering tissue architecture. 3D printing is heavily used in this field of tissue engineering. It's not like, it's about developing new polymers for tissue engineering applications, or it could be developing new 3D printing machines and stuff like that. And then different cross-linking methods for the polymers are being used. There are a lot of applications that chemical engineering knowledge can be applied. So what I'm trying to do here is I'm just want to show you these applications are there. If you think you like a certain application, please go ahead and search in the internet. You will see more information. And then sometimes for tissue engineering, we use decellularized organs, which means we take organ, and when we kill all the cells, or we remove the cells in this organ and trying to create novel tissue with this decellularized organ. So there are these kind of applications, and this is how cells engineering, materials and engineering tissue architecture development methods come together to create an organ that can replace damaged tissue. And to talk more about how this is being done, obviously we are talking about cell culture. Then there will be different bioreactors involved. And this is a field that we can contribute. Bioreactor design. In a bioreactor, it's very important we control the nutrient or the oxygen transport within the bioreactor. And so these are the things, the concepts of mass transfer can be applied, the energy transfer can be applied. And then if you are into mathematics sides, you can look into cell growth kinetics, how cells will grow within a bioreactor and how different growth factors would impact the cell growth kinetics, things like that. And as I mentioned earlier, there is 3D printing and scaffold design. So this is a huge area. If you really want to work on this area, there are like a lot of opportunities. And then there is one important thing, mechanical testing of those created tissues. Imagine if you are going to replace your ear with a tissue engineered ear, it should be able to, like, it should not be deformed after you sleep on it, right? So you should be able to wear a helmet, headphones, or things like that. So it has to undergo certain loads. So this tissue engineered ear also should have the capacity to bear up those loads. So you have to think about those things. And there are different mechanical testing methods are being used to test those tissues. And this is one area that we can use, especially in cartilage tissue engineering. I want to tell mechanical testing is very important. And as I said, then there is biomaterials development. So this is about tissue engineering. I think now you can see how the concepts of chemical engineering can be applied in tissue engineering. And then I want to talk about another application of tissue engineering, actually. So this is not related to biomedical engineering, but this was derived, like it was taken from biomedical engineering, cultured meat or leather. So this is all about creating meat without killing the animals. So this is basically taking cells from a cow or a chicken, and then you culture in a lab, and then you will end up with some beef or chicken burger at the end of the day, and you haven't killed any animals. So there are cultured meat companies emerging around the world. I know in Australia there are 2 companies, and yeah, so around the world there are different cultured meat and leather companies. I just wanted to show you because this was related to tissue engineering, and this is also called as cellular agriculture. So if you want to go into these sites, that's totally fine. Like it's a really emerging field in the world. And from the next slide onwards, I will go into like my PhD research was related to cartilage tissue engineering, but I will not talk about it today. But at the end of the talk, if there's going to be any time left, I might talk. But now I'm going to show you other applications, the other areas of biomedical engineering that we can use our skill set as chemical engineers. So one is prosthetics and implants. So medical implants are devices or devices that are placed inside the body, and many implants are being developed to treat different conditions. So think about the hip joint, like this is, as you can see in this prosthetic, this is the implant to hip joint, implant to replace the hip joint. So hip joint can be damaged due to many reasons, which I'm not going to talk about here, but you can see if you look into this implant, you have different parts: femoral stem, plastic line, and acetabular component. And think about designing this kind of implant. This implant has 3 different parts, and what materials should be used, and what should be the design, and is there a way to personalize or customize the design, because my hip size is different from someone else's hip size. So the results would be optimum if this implant can really made into my measurements. And then you have to think about the aspects like load bearing capacity of this implant, because the hip is a place where we are going to move a lot. So you have to walk and run. So what is the endurance? And those kind of aspects should be considered when selecting the material. And as chemical engineers, we know we work with different types of materials. We know how to test materials, and we know what material properties to be looked into. And those are the things that we have. Those are the things that we have to use when apply them to biomedical applications. And also one other thing is osseointegration, which means, as you can see, this femoral stem is put inside your bone. Like after some time, the surface of this femoral stem will integrate with the bone. So this is called as osseointegration. For this process, there are like different surface treatments that should be done to those implants to promote this osseointegration. So this is another cool area. So how to promote this osseointegration and how to modify the surface of the materials. And then there are a lot of research going on with infection control, which is about how to control the infections related to these prosthetics. For an example, like there are like nano materials, like nano coatings are being developed to coat on these kind of implants to reduce the risk of infection. And there are a lot of manufacturing processes that will be used in biomedical industry and the related standards. It's a really important thing as process engineers. So the standards and specifications and the regulations related to biomedical industry is different from the normal regulations that we know. So there is another area that we can contribute our knowledge, manufacturing process. And then we also have to think about the long-term effects when selecting materials or designing those things. Imagine after sometimes you see any implant here, after a few years, what happens if this metal is going to be brittle and particles are going to be in the patient's body? There will be a lot of issues. So there are a lot of factors that should be considered when it comes to biomedical applications. And then we have to select the best material and the best design. So we have the skill set to do this. We just need to learn a little bit about the human body or the specific application. So yeah, this is one example. And then I have another example, heart valves. So that something goes wrong, there are like different heart valves being developed. So I have listed some factors to be considered here, which is different from the previous example, to show you the difference between one application and another application. So material selection, it's important as previously, and size of the valve and the sound effect. So what does this mean? You know, in the heart, the valve, we hear this loud up sound because the valve is opening and closing. Imagine we develop a nice heart valve, and then we implant it in a patient. And what if this valve is going to give an annoying sound? So like the patient would not be able to sleep, and those kind of factors will be affect the quality of life of the patient. So we have to consider those kinds of aspects or factors when selecting materials and when designing certain implants. Yeah, sound effects is could be a huge issue when it comes to a heart valve. And also we have to think about the surgical handling. So this is another aspect. So as we engineers, we might design something, but it is a doctor or a surgeon who is going to implant it. And it should be like, the surgeon should be able to implant it easily. So we have to think about the aspects of surgical handling as well, and the durability of this material, or the design, because we are talking about heart here. If something happens, you die. It's heart. You can't live without your heart, right? So yeah, so these are some of the key factors that you might have to think. And there are a lot of other things like biocompatibility and those things, but I'm not going to talk about those. But I just want to talk you through some factors that you will that is easy for us to understand as chemical engineers. Yeah, so this is about heart valves. And then I have another application, a dental implant. So in dental implant, so you has three parts as you see in this diagram. But think about what other aspects you have to think. Like previous two applications were like internal, but this is something external. You can see my teeth when I talk. So you had to think about the color of the crown, like the tooth. It should match the color of the other tooth. And what are the long-term effects? Like will this crown or the tooth will remain in same color after 10 years of time, or it needs to be replaced in every couple of years? And you have to think about the hardness of the material and what the patient should eat. Like, yeah, sometimes we eat hard materials, like can it crush this crown? And how is things going to be with acidic food like vinegar or something like that, and risk of infections. So these are the factors that you will consider when you think about implants. And there are a lot of applications. So what I want to understand, I've showed you three different implants, and the aspects were slightly different from each other. So in biomedical engineering, it's very important to understand you might be specialized in one type of thing, like maybe you will be specialized in heart valves and related things. Someone might be specialized in hip joints or knee joints, things like that. So it's because you have to know everything about these implants and design. So that's why you have to be specialized. And also you have to collaborate with doctors, engineers, and many other people from different disciplines. So this is about prosthetics and implants. Then I want to talk you about some other medical devices or equipment. So I went through some of the medical devices where we can see chemical engineering applications, and I decided to select two which I seem relevant to Sri Lanka as well. I'm pretty sure you have heard those names: ECMO machine and dialysis machines. So I'm going to talk about those two medical devices in next few slides. Yeah. So in this diagram, like this is a schematic diagram of an ECMO machine. So I would say, with my experience, the whole chemical engineering design subjects are there. So for an example, you can see there's a heat exchanger to keep the blood warm. And then there is a membrane oxygenator to supply oxygen to the blood and remove carbon dioxide. And then there is pump, and we are talking about the flow of blood here. So these are different aspects, so different chemical engineering design aspects that we can use in biomedical engineering devices. So designing membranes. So please go ahead and see what are the types of membranes used for this kind of machine, and what are the different types of techniques they have used to improve the efficiency of the material transfer and fluid mechanics, and then Yeah, I'm pretty sure. I'm not sure how many final years are there, but in final year, I know there was not, maybe not in final year, but the pump selection and what kind of pumps to be used and those kind of aspects uh, are really important when it comes to the biomedical applications as well. And heat exchange design, yep, I think it's the third year subject or fourth year, I can't remember, but this is something we have done. And this is simply another application. And when it comes to biomedical applications, there are other things we have to think about, like maintaining aseptic conditions or reducing contamination, things like that. But other than that, the principles that we apply are similar. Next, I have another, yeah, and this is a schematic diagram of a dialysis machine. So it's somewhat similar to the previous example, and you can see there is a blood pump, and then there is a dialyzer. And our knowledge comes in designing how to create this dialyzer or this filter that they are talking about. A lot of material transport and energy as well, because we have to keep the blood warm as well. Imagine the blood is going out and its blood is going back to the patient, and our bodies are at temperature of 37 degrees of Celsius. So it's very important to maintain the heat as well in these applications. So if I ask a question, what is the difference between ECMO and dialyzer when it comes to the material transfer? So the main difference is in ECMO, we are giving oxygen to the blood, and here we are taking things from the blood. So these are like into the system and out of the system. So what separation process to be selected? So these are the things that we learn. So, and I think it's for you, it's evident how you can use these concepts in real world to solve clinical problems. And then next slide, I'm going to talk about another application that we can contribute. It's actually microfluidics. Maybe some of you have heard it. This is a very, I would say, a hot field in now. And so microfluidics is basically the manipulation of fluids in channels with dimensions of tens of micrometers. So here we are talking about channels of 500 nanometers to 500 micrometers. The most important, why the microfluidics is important. Microfluidic devices exploit the physical and chemical properties of liquids and gases at microscale, which means in microscale, fluid behavior is different from macroscale behavior. So the laws that you might know in designing a pipe flow or determining the flow rate of a pipe would not cannot be applied in this kind of application. So, so you have to consider the factors such as surface tension, energy dissipation, fluidic resistance, and things like that when it comes to this kind of application. I don't have any experience with microfluidics, but I have seen a lot of nice applications in this field. And I also want to highlight a thing like chemical engineering. We were thinking about scaling up things when it comes to chemical industries, but when it comes to the applications like this, and now there is a trend to scale down things. And one application is personalized medicine and stuff like that. Now scaling up as well as scaling up as well as scaling down is important in the field. So I have a video about microfluidics in next slide, and it explains a lot of applications and its strength. So one application is image processing. Could not be like hardcore chemical engineering, but during my PhD, I had to learn and apply the principles of image processing. And so it could be a really good area if you're into mathematics and if you are into coding a lot. And image processing research is huge. It's really huge. And then you can work on applications like contrast agent development. So this is kind of related to biomedical imaging as well. You know, there are different types of biomedical scanners like MRI, PET, like different scans, CT scanners. So for these ones, sometimes the contrast agents are needed. So you can, with your chemistry background, you can develop different contrast agents. And then there is biomechanics. It's all about analyzing the movements of the body. You can, like, if you are into analyzing forces, things like that, you can work on biomechanics, and there are a lot of applications out there. And then there is mechanobiology, which was kind of related to my PhD as well. So mechanobiology is understanding how cells respond to physical forces and react. So imagine the cells at cartilage. So understanding how cells in cartilage tissue respond to mechanical forces is very important for tissue engineering applications if we want to replicate the same tissue in a laboratory. And then there is biomedical material development or processing. I might have touched this field when I was explaining other applications. There is a lot of, there are thousands of biomedical materials that you can work on, and it depends on the application as well. So it's a very big industry, as well as a huge research field. And there are more and more. So you can keep working on these things, like just go and search. If you're really into biomedical engineering, please go and search the applications and stuff like that. You will come across even cooler applications cool applications than what I have shown you today. So the second last slide, take home message. So I intentionally left this slide blank, but I will go through what is the take home message is. So chemical engineering principles are widely used in biomedical applications. This is what I want to understand from today's talk. And you can choose the area what you want to work on depending on your interest. There are a huge number of applications. If you think biomedical engineering is your passion, go search and find the niche you like. If you want any ideas or inputs, please contact me. I'm happy to share what I know with you, but if I don't know about a particular field, I know someone who knows about certain applications, and I can direct you to those people. Oh, yep, and the last slide, perhaps the most favorite slide of all of you, it's thank you slide. So thank you very much for listening, and thank you very much for giving me this opportunity. I hope you learned something new today, and I'm happy to take any questions.
Thank you very much, sir, for the valuable and insightful address to our topic today, chemical engineering in biomedical engineering. That was thoroughly enlightening and inspiring for all of us. And I am pretty sure our audience learned a lot from you. Here's the time for another interesting segment, the Q&A session. Dear audience, we are ready to give you the opportunity to raise your questions. You can either raise hand option or chat box to send your questions. I will narrate your questions to Mr. Manula Rathnayake. I hope everything is clear and this opportunity is yours to get your doubts clarified and enrich your knowledge.
Like if we come up with a research in the laboratory, and then let's say that it passes all the toxicity tests, it passes all the cell in vitro tests, but then there can be an issue when it goes to if we are, let's say we're talking about an implant, and then if we use this implant in a human or an animal, there can be issues complications that arise there. For example, inflations and such. So are there any like issues or concerns with respect to the ethics and security there that we have to know of?
Yeah, it's a really good question. So as I said, like you will develop things in laboratory and you will not first take it into the humans. So you will first take into the animals trials, as you may know. And at animal trials, you will try to identify the related complications, and the experts in the field will assess them. So they will be writing reports and they will be assessing the different complications of these devices or drugs or whatever they think. And then once they review the results of animal studies, and if they think they are promising, they will move into human trials. So this is a huge step from animal trials to human trials. And I want to know that, I'll let you know that when it comes to human trials, it could fail. So there is this risk. You might have done everything correct, but for some reason it could fail. So actually we haven't understood how our bodies work yet. Like completely, we don't have this knowledge. So there could be different reasons. So it could really fail. But there are a lot of regulatory bodies around the world. If you talk FDA in United States of America, or it's TGA in Australia. So they have a lot of regulations and guidelines when it comes to bringing up or registering a new medical implant or a medical device. So they will review whether the people have done, like the researchers or the companies have done relevant research and studies before giving the approval. So there is a risk, but there are regulatory bodies looking over these activities. But even after the regulatory approval, there are cases that has, like, there are devices or the materials or the implants that have failed even after the regulations and the product has been recalled. There are a lot of issues like that. It might not be related to the designing issues, but could be contaminations and other issues. But the simple answer to your question is yes, there are a lot of regulatory bodies overlooking these activities. So these regulatory bodies are trying to minimize the risks of those implants or the devices. I hope I answered your question.
Yes, yes, sir. Thank you.
Dr. Nadish is raising hand. So you can ask question.
Right. Hi, Manula. It's Nadish here. Can you hear me?
Yeah, I can hear you, Nadish. Yeah.
Right. First of all, thank you very much for accepting our invitation and giving us a very insightful talk about, very modern fields like interdisciplinary fields like biomedical engineering and its applications. Right. This is actually related to tissue engineering. This is this question, very quick question that I wanted to clarify. You mentioned that when we do, the implants basically use stem cells and growth factors and scaffolds. So,
yeah.
So basically, I was wondering about the, one of the major concern or the major challenges we have when we do implants, that the compatibility issues. That's what we have heard, right? Though you find a donor, sometimes you have a lot of the other factors which restrict a successful implant. So is it possible when we use this sort of 3D printed organs, like does it minimize that compatibility issues? And the next question, so I will ask, I have two quick questions. The second one, I was really interested about the scaffolds. So you mentioned about scaffolds. So I was wondering, just for my knowledge, like when you target for different types of organs, like it can be a cartilage base or it can be active organ like the liver or heart tissues, whatever. So then each and every cases, do you use scaffolds or let it dissolve with time, or is there any the cases that we do not use scaffolds, like directly you use it and get the the printing done? So those are the two questions, just for my knowledge. Thank you, Manula.
Yeah, thank you, Nadesh, for your questions. Yeah, the first question was related to the compatibility issues. If we take the cells, from the patients, the rejection, like the immune reaction, the risk of immune rejection from its body is minimized. That is the goal of tissue engineering, like to take the cells from the patient and use them. So this can avoid this rejection issue, because that's why at the beginning I said there is the option of organ transplantation, but we have to find a suitable donor, which is not easy within the time frame. So using the cells from the patient can reduce this risk of rejecting the tissue engineered tissue or the organ. However, depending on there are other factors, like as you said, there are scaffolds. If you're using scaffold, sometimes this scaffold could trigger immune reaction. For this one, we have to test those biomaterials for a long time and to see how this material is absorbed back to the body and over time. So there are like a lot of research going around this area. So yes, but using the cells from the patient reduces the risk of rejection of this novel or tissue or the organ. And I want to highlight that tissue engineering is comparatively novel field. So we are not at the stage of replacing a kidney or a heart or thing like that. So still we are trying to get things done with cartilage and simple tissues, because if you think about cartilage has no blood vessels and no like nerves, which means it is relatively a simple tissue, because imagine if you are going to deal with some other kind of tissue, there are blood vessels and neural tissue that we have to create in the artificial tissue as well. So even in the cartilage, currently the most challenging problem is not like getting the tissue with the good mechanical compatibility. So there is those kind of issues in addition to these rejection issue. But the simple answer is the compatibility issue can be reduced using the cells from the patient. And the other one is, other question was, is every time we have to use the scaffolds? The answer is no. There are other tissue engineering techniques that we don't have to use scaffolds. Sometimes you can culture the tissues into 2D sheets and stack those 2D sheets one over each other. But all these things depends on the application and which type of the tissue. So are there techniques that doesn't need any scaffolds? Of course, there are techniques like that. Yep, I hope I answered your questions, Nadish. Oh.
Yeah, Manu, thanks. Great, thanks. Thank you.
Okay, cool.
Dear audience, you can ask your questions through the chat box also. There's a question in the chat box. How can a chemical engineering student integrate with biomedical engineering in Sri Lanka?
Yes, it's a very good question. Perhaps I might not be the person to ask this question, but I can say, like, I did chemical engineering in Sri Lanka, but then I moved here to do biomedical engineering. I know that at the Morato University, there is this biomedical engineering bachelor's program, but yeah, I don't know anything other than about that. I'm so sorry, but maybe you can work in the fields like regulations and stuff like that. If there are any biomedical companies, to be honest, I can't, Bimsar, I'm so sorry, I can't give you a direct answer for your question.
So there is another question in the chat box. Is tissue engineering technology hints on developing a fully synthetic human body in future?
Yes, a very interesting question, Yasindu. Thank you very much. Well, never say never. So yeah, it could happen, but I would say we are far, far away from this goal, because currently, like, still, like, tissue engineering is still working on tissues like skin, blood vessels, and like more simple tissues or cartilage. So yeah, if things go well, it could happen, but I don't know, it's far, far away, not in my lifetime or your lifetime, it's far, far away in my opinion. So yeah, it could happen one day, yeah. Any other question? It was a really interesting question.
Sir, can I ask a question?
Yeah, sure, go ahead.
Yes, sir. So this might be a general question because when the first impression that we get when someone says that they are going for a PhD is that one day that they will be working as a lecturer, and in most probably in Sri Lanka, in the environment that we grew up in, the most common thing that we see of a person who has done a PhD is that they are becoming a lecturer later. So, so can you please elaborate what the duties and responsibilities that a person who's in the industry with a PhD has to do in case of your experience and anything?
That's a very good question, Placido. I'm glad that you asked this question. So that's what you said was correct. So the impression, even when I was in Sri Lanka, was if you have a PhD, you will stay in academia. So academia is the place where the research is done and new knowledge is created. But when you go to like outside of Sri Lanka, Europe, US, Australia, anywhere, there are a lot of PhDs being offered. If all of these people are going to stay in academia, there will be no space. And a lot of people don't want to stay in academia as well. For an example, me, I decided I don't want to stay in academia. I want to move into industry and work on some kind of job like. So in industry, what PhDs has to do, so there are specific jobs that the minimum qualification to enter this job could be having a PhD. Like it could be very specific applications and stuff like that. So yeah, so there are these kind of jobs. And for my experience, I know, there is people called patent attorneys, like the people who write patents. I don't know how it is in Sri Lanka, but I know in Australia, to be like patent attorneys I have met have a PhD in a very specific field, and they have some degree in law as well. So they have a scientific and law background as well. So this is one area that PhDs can work. And so currently I'm working as a research and development consultant. So what I normally do is I look into research done by different companies and trying to understand what is the hypothesis, what is the new knowledge created, and things like that. And then in industry, even with a PhD, you can go and work as an engineer. So I know friends who work as like project managers and engineers in the industry with PhDs. It all comes down to the skill set you acquire through a PhD. And yeah, industry will highly value this skill set. No, unfortunately, not in Sri Lanka, but in other countries, there are a lot of opportunities. So yeah, just search what opportunities you have, and if you really want to do a PhD and go to industry, you can do it. Yeah. Did I answer your question, Pasindu, or do you want to know more?
Yes, sir, you did, sir. Thank you very much, sir.
Oh, okay. Thank you. My pleasure.
So there's another question. What's the success rate of cell transplantation for spinal cord injury?
Yep. Hi, so sorry, I can't give you a specific answer for this question. First thing is, I'm not familiar with this specific application. So I'm so sorry, I can't give you an answer because, yeah, I can tell something, but it's not going to be correct because, so I don't know the answer simply. I'm so sorry, but yeah, if you really want to get some answers, I can direct you to someone who might do research in this area. I'm sorry about that.
Dr. Charita, madam, you can ask the question.
Hello, thank you, Manula. It was a very interesting presentation. So I have a very basic question. So the question is, if someone is planning to do a PhD, we all know that to get admitted to a PhD, you need a specific GPA and you need X number of publications and things like that. But apart from that, what skill set should a student develop if he want to transition to doing a PhD?
Yeah, the skill set is learning by yourself. Like you have to learn how to learn. So in my experience, like even when I was undergraduate, I was trying to do things by myself, but I do see this trend in faculty. The students are trying to rely on another student. It could be for exam or anything like that, as in like they will not study by themselves and student will not investigate how to find new knowledge and stuff like that. So if you are moving to do a PhD, the very important thing is like self-motivation. You should manage your own work and you should decide what you do, like the decision making and stuff like that. So the first thing during my PhD, everything I have learned, I had to figure it out by myself. My supervisors, of course, they helped, but when it comes to the knowledge gathering, it was done mainly by myself, reading papers, books, and talking to other people. The supervisors will guide you, but you have to find your own way. So to find your own way, you have to know how to find it. It is all about learning new stuff by yourself, and this is a very important skill you have to develop. And the most important thing, Pat, is staying mentally strong. So depending on your circumstances, you might go through like a lot of hardships during a PhD. Stress handling, this is very important. So yeah, I would say these are the like key skills that a student should develop. Yeah.
Okay, thank you, Manula.
Thank you very much, Dr. Charita Gamlat, for asking the question. As well as Akila Lakshan is raising hand.
Yes, can you hear me?
Yeah, I can hear you. Yeah.
Yes, sir. Sir, since we have been talking about this tissues and related stuff, I would like to know that whether there have been any successful attempts to achieve the photosynthesis inside the laboratory. Have anyone been successful for that kind of things?
A good question, Akila. But when it comes to the photosynthesis, it belongs to not like biological. It's a biological, but it's more like plant biology. So I do not have any experience about this area. So unfortunately, I couldn't answer your question. Sorry about that.
Okay, sir. Thank you, sir.
Dear audience, you can ask any other questions also.
I have one last question. If we are to pursue a future in biomedical engineering, is there an extent that you recommend that, let's say if you are studying about the human body, that we should know, because like we can't learn everything related to the biological aspect. But...
Yeah. A very good question. So yeah, of course, like for an example, in tissue engineering field, a lot of people I have met have degrees with chemical engineering, and they might know something about the physiology and stuff like that. Yes, imagine if you know you are going to work on knee joint, you will need to learn the knee anatomy and stuff related to that only. So you don't need to learn about the brain or other stuff like that. You can restrict your knowledge to your application. If you're going to work on ear, you can just restrict your knowledge to this part only. So it's like that. And as I said, this is a multidisciplinary field. So there will be doctors, there will be other people who collaborating in this project. So if there is anything specific that we might miss, they will catch it up. So I would say, depending on the application, you can restrict your knowledge of biology to your application area or the anatomical area that you are working on.
Okay, thank you.
Is there any questions?
I have one more question, Manula. So, yeah, so you directly went from chemical engineering to biomedical engineering. Is there a specific aspect of you that your PhD supervisor was interested in before hiring, like any biomedical related thing that you knew before transitioning into the PhD, or your fundamentals were really good and that's why your supervisor selected you? Is that?
Oh, yeah. Yeah, it's a very good question. So it all comes down to what type of research that I carried out. So I had wet lab experience at University of Peradeniya. I was using HPLC and stuff like that. Was not related to biomedical engineering, but it was those lab skill set and my chemical engineering background. As I said, in the field of tissue engineering, that like many chemical engineers are working in this field. So yeah, so they know that our skill set is useful in the tissue engineering field. And personally, I didn't know what was cartilage. I mean, of course I did know what cartilage was, but I didn't know anything about biomedical aspects of cartilage or things like that. And even the jargon, it was at the beginning for me, it was a little bit challenging to get the words first because we are not used to those biomedical or medical terms. But other than that, so in my case, it was purely chemical engineering, wet lab experience that I used to get hired. Yeah, and it could depend on your project that you are applying for. So it's no direct answer, but in my case, it was my wet lab experience.
Okay, thank you, Manu.
Are there any questions? There were so many questions. I think the topic is very interesting. So the questions are over, I think, now. So thank you very much, sir, for sharing your invaluable experience gathered in your exemplary journey so far. Your explanations for our questions were easily understandable and valuable for everyone. We are now certain that our students are aware of another engaging path they can undertake as chemical and process engineers. And I would like to invite Mr. Hasitha Eranga, the co-chair of isotopes of the Society of Chemical and Process Engineering students, to propose the vote of thanks.
Hello, good evening, ladies and gentlemen. I hope you can. I'm audible. Am I audible, Sachin?
Yes, you are audible.
Good evening, ladies and gentlemen. It is my honor on behalf of SCAPS to propose vote of thanks and acknowledge the contribution of everyone, those who dedicated their time and energy to make today's event very successful one. First, I would like to express my gratitude to our guest speaker, senior graduate Manula Rathnayake, not only sharing his valuable time to share his experience transforming chemical engineering into biomedical engineering, but also motivating us to think beyond the reality. Thank you, sir, for putting your best effort to make this event success with your commendable talk. Next, I would like to thank our beloved academic staff of Department of Chemical and Process Engineering for their valuable contribution and encouragement in our all efforts. Last but not the least, I thank all the participants who joined us today and the committee members of ESCAPE for organizing such an astonishing event. Thank you all for your attention and stay safe. Thank you.
And thus, we have come to the end of this amazing session. Hope you all had a wonderful time with us. Thank you everyone for joining us today amidst your busy schedules. So with the hope of meeting you again on another memorable day with an inspiring topic, it's time for us to wind up the today's session. Good night, everyone. Stay safe.